Dr. Sabhapandit might have mentioned that I have some urgent work, so I have to cut short my stay here. So I'm going to take 2 classes in succession, if you can survive or I can survive. But I'll give a break and try to go very slow. The tutorial should be made up tomorrow. Okay, so if you recall, yesterday we started discussing dissipative two-state systems. So we have a general situation where you have a Hamiltonian, which is perfectly genuine, innocent. It is Hermitian, therefore it has unitary evolution. And in general, and this is what is called a system plus bath approach, where you split the total Hamiltonian into 3 parts. A part which deals with the Hilbert space of the system alone, then a part which deals with the bath alone, and then you have a coupling term or interaction term. So this is a generic situation, and our whole idea is to average over the bath to discover properties for the subsystem or the system of interest. And if you remember that this is the way we do experiments, right? For instance, I was talking about, let's say, hydrogen diffusion in metals. Now, hydrogen is a very light particle. Hydrogen is a light particle, so it can actually move very fast in a system. And in fact, it undergoes what's called quantum diffusion. And to study this problem, suppose you have a hydrogen atom or a collection of them. And one of the very important methods to study hydrogen is neutron scattering. So you come with a neutron beam from a thermal reactor. Okay, and then you look at the scattering. Okay, so the neutron, of course, is a nuclear particle, and hydrogen has its proton, and there's very short-range nuclear interaction, a Fermi contact interaction. Of course, there's also a spin interaction because the neutron is a spin-half particle, proton has a spin-half. So there is also a spin-spin interaction, but suppose we ignore the spin part, the dominant interaction is this nuclear interaction. And so the point about the subsystem is that, you see, so by the very nature of your experiment, you're probing a subsystem of the entire global system, because this guy is in contact with many other degrees of freedom, like electrons, phonons, etc. Now, neutron being a neutral particle will not interact, let's say, with electrons electromagnetically, and not directly with phonons, or even if they do, they'll be at a different frequency range. So by the very nature of your experiment, you pick up certain degrees of freedom, which you want to lump into what you may want to call the subsystem. However, The scattered neutron, of course, carries with it the information about the dynamics of hydrogen in the heat bath with other degrees of freedom. So they are all there. And because in the measurement you do not observe the other degrees of freedom, you must sum over all of them or average over all of them. So the very nature of your doing any experiment is something that allows you to make this splitting mentally. All right? You can think of a nuclear magnetic resonance experiment where again you look at either a proton or a carbon NMR, etc. Again, what you do is you apply a magnetic field, and of course the magnetic field will couple to both electrons and the nuclei. But the nuclei has a nuclear magneton and the electrons have Bohr magneton. So the difference is the mass ratio of the proton and the electron. And so in one case you measure, that is in the case of the nuclear magnetic resonance, you measure properties in the radio wave range, radio frequency. Radio frequency is like 10 to the 6 second inverse. On the other hand, for the electron, you have 3 orders of magnitude higher frequency because the Bohr magneton has a mass downstairs. And so that's like microwave, like 10 to the 9. So, in your frequency window, either you observe nuclear resonance or you observe electron resonance, and hardly ever you see an overlap. So again, by the very nature of your experiment, if you do NMR, you pick up that nuclear Zeeman interaction. If you do EPR, you pick up the electron interaction, etc., etc. So all spectroscopic experiments, most experiments, or atomic force microscopy, whatever, will selectively pick up degrees of freedom. And the rest, of course, are in the thermal cloud around, and they indirectly, of course, influence the results of the measurement because this guy is in interaction with them. Interaction cannot be switched off. So this is the basic philosophy, and we discussed under this basic philosophy a few examples. For instance, the spin lattice relaxation problem, which is how you magnetize a system. In this case, your Hs is really the Zeeman Hamiltonian. I'm putting all factors equal to 1 times, let's say, if I do electron spin resonance, let's say I times sigma z, H times sigma z. So that's your subsystem Hamiltonian, very simple one. The bath could be a bath of phonon, so you write independent harmonic oscillators. So H bar omega k, bk dagger bk, and you assume a very simple linear coupling which couples to the linear coordinate of this. The linear coordinate, see, normally coordinate, of course, is a infinite dimensional vector in the Hilbert space, but in this problem that infinite dimensional vector space has been shrunk into a 2 by 2 space for the spin system. So you have, but you want to have spin flipping of the kind that we talked about yesterday in detail about the single spin flipping problem. And so as you saw yesterday, that you put in a simple coupling which is of this form. Now this coupling is the same coupling as far as this term is concerned as you saw in the Swansig-Ford model in the context of quantum diffusion, and because BQ plus BQ dagger is like the position coordinate of the kth mode of a harmonic oscillator, apart from some factors, right? And this term is a free Hamiltonian, which is like pj square over 2mj plus half m omega j square qj square term, which you write harmonic oscillator in terms of the boson creation annihilation operators. You get that form. Is it clear? So the whole idea is that if you now move into a frame where you move into the frame of the bath, in that frame, this BK dagger operators become time dependent, right? For instance, BK of t is given by e to the power I h bath over h bar times t, BK of naught e to the power minus IHB of t over h bar. And because it's BK dagger BK, that doesn't commute with BK or BK dagger. And hence, you will develop time dependence, like what you do in the interaction picture. So what is happening is that these boson fields are being jiggled by the harmonic oscillator term, and they give you oscillating terms, right? As you know, that when you work these commutators out, which I'm going to do soon, you're going to generate things like cosine omega k term, omega kt, sine omega kt, etc. So they actually, these terms oscillate with the characteristic frequencies of the bath variables. And when these oscillations are very rapid, or when you have a whole lot of modes superposed, as you know, if you superpose a whole lot of Fourier modes, you can generate random noise situation, especially over time scales where these frequencies are considered to be very large. The bath variables frequencies are very large compared to the frequency of the system of interest, which is given by H inverse. And so the whole idea is that, like you know, that what this term does is to cause the spins to lie more precise around the magnetic field. The precession frequency is proportional to H, and if that is smaller compared to these jiggling frequencies, then by the time the spin makes one Larmor precession, it is perturbed so frequently by the bath variables that those perturbations appear to be dissipative, and we saw in what sense they appear to be dissipative when we worked on the quantum Brownian motion problem. Now, suffice it to note at this stage that in general, the splitting makes sense only when Hs and Hb commute with each other, as they manifestly do in this example. Otherwise, it will not make any sense to split them because, and of course, Hi commutes with neither Hs nor Hb, and that is the whole idea. So that's like a coupling between the two systems. So if you have Hs as a small system, Hs, and then you couple by Hi to a rather large system, which is your heat bath. Okay. So if that is so, that you know in quantum mechanics, that if two operators commute, in this case two Hamiltonian operators, then you can go to a representation in which both Hs and Hb are simultaneously diagonal. And so it's easy to work in that representation in which Hs and Hb are diagonal. However, Hi would be off diagonal, and that will be the interesting physics that will be introduced through the coupling term. Okay. The other kind of problem that has been looked at extensively is tunneling in a symmetric well. Here is a symmetric double well. And if you leave a particle here, then that will keep tunneling back and forth. Actually, if you look at the book by Metzbacher, he it does in detail a problem called a double oscillator. A double oscillator is a harmonic oscillator like here, whose origin is not at x equal to 0, but let's say at x equal to plus a, and you put that in juxtaposition to another oscillator. X equal to minus a. And Max-Bachert solves this problem in the WKB approximation. That approximation makes sense when this barrier is pretty high compared to the small oscillation frequency in either of these wells. See, if you have a particle here, at the bottom of the well, it's like a harmonic oscillator, so you'll keep on doing that. And now the question is, how does it tunnel? And this is an interesting problem. I recommend that you read Max-Bachert's quantum mechanics book. It's an MSc level textbook. And so you can ask the question that what would the energy eigenvalues of the double oscillators look like as a function of this parameter A, right? Which is basically 2A is a separation between the two minima of the two oscillators. So now you should be able to answer this, what you expect to see for, let's say, A equal to 0. For A equal to 0, the two oscillators collapse into a single harmonic oscillator, right? Right? For A equal to 0, I don't have a double oscillator. I simply coalesce them into a single harmonic oscillator. And for that, you know the energy. The energy of a single harmonic oscillator, as you know, is half h bar omega times n plus, well, h bar omega times n plus half. So you have the ground state energy, which is half h bar omega. So assume that the curvature is the same for the two wells, so you have the same frequency. The next energy level is what? 3/2 h bar omega, right? Then you have 5/2. They're all equispaced. 7/2, etc. And now what will happen if A becomes very large, infinitely large? It means that I have taken the two oscillators and pulled them apart, and where each one is infinitely removed from the other one. So what do you expect there? You would again have two independent harmonic oscillators, and therefore also have a degenerate, right? Because the two oscillators don't talk to each other now. So you, as Max-Bachert shows, that what you will see is a collapse. So h bar omega, so the two oscillators, the ground state will look like this. And so they will collapse pairwise as A becomes very large. Now if you are in this regime, that is, your A value is such that you're actually looking at very narrow energy separation, and also if your temperature is very small, so that you don't Boltzmann occupy the higher energy levels, then the system is now in a truncated Hilbert space where you only have to consider these two, this energy splitting, and that's the tunneling frequency. So that's the tunneling frequency, which means that the particle will keep tunneling back and forth, and you can see that phenomenon by doing the neutron scattering. So you can see why a double oscillator near the ground state actually can be described in terms of Pauli spin operators, because it's a two-state problem. It's an effective two-state problem. This is what you could continue to do in condensed matter physics, because at low temperature, then you don't have to worry about higher energy levels. Like In the diamagnetism problem, everything is now in the lowest, at very low temperature, everything is in the lowest Landau level, and that's where quantum Hall effect becomes very interesting. Okay. And so how do you describe this tunneling term? Well, you can say that as far as these two low levels are concerned, I will, so basically that's the tunnel splitting, and I'll map the left well as sigma z equal to +1, right well as sigma z equal to -1, and tunneling means transition between these two, and I need therefore an operator which is purely off diagonal in the representation in which sigma z is diagonal. And so my subsystem Hamiltonian now can be written as delta times sigma x, where delta is indeed what is called the tunneling frequency. It turns out that, I'm not going to describe this in detail, but it turns out that when you have this truncated system, what you observe in neutron scattering is both side Fourier transform of this kind of spin correlation function for this model. And so when you have tunneling, that is only this term is dominating without the coupling term, then what you measure is a neutron structure factor S of k comma omega, and you actually see two lines at omega equals plus delta and omega equals minus delta, and that is due to coherent scattering, and gives you inelastic lines. Why inelastic? Because they are not at omega equal to 0. At omega equal to 0, you have this elastic scattering called the Rayleigh line, and you have these two lines. And why is it that the one has higher intensity than the other? And that's because of the Bose-Einstein factor, which is why the Stokes and anti-Stokes lines in Raman scattering have different intensities. But now you bring in dissipation, because in this physical problem, like hydrogen in niobium, for instance, or hydrogen in metals like niobium, such as niobium, you have an electron cloud around the proton. So you have strong Coulomb interaction. So as that thing tunnels, it interacts with those Coulomb interactions. And you want to model that and to mimic that. And so that modeling can be done exactly the way we have written down. But since now it is delta sigma x, you have a sigma z kind of coupling, summation q or k that I'm writing, gq bk plus bk dagger, and you have the same Bath Hamiltonian. So again, this term will be jiggling around, will jiggle sigma z, and that would cause transition in the eigenstates of sigma x. You can also diagonalize sigma x. And therefore, tunneling will become incoherent. And so, so this is what you see in the experiment at ultra low temperature, like 5 Kelvin or so. And as you increase the temperature, these lines merge into a single elastic component. It's not exactly elastic because it has got a width, and that's why it's called a quasi-elastic line. So it's still not classical because you have been able to suppress the coherent precessional or coherent tunneling terms which have given you the inelastic lines. But so you're going into the quantum classical like regime, but you're still in a damped system, like you've been hearing about over-damped limit. So it's like the over-damped limit of the tunneling problem, where you can experimentally you can measure this width of this line, or full width at half maximum or whatever. And what is very interesting in this situation is that when they plot the width versus temperature, they found that the width is actually going down in temperature. See, if I were dealing with a classical particle at a sufficiently high temperature will go across the barrier by a process called thermal activation, and that activated process goes with a rate constant lambda naught times e to the power this barrier height over kBt, the so-called Arrhenius formula. So you see what happens is as temperature T increases, this factor becomes smaller, and you have an e to the power minus that. So you have an increase in the rate of jumps as you increase the temperature in the classical problem. So in classical physics, the width actually increases with temperature. That is how you measure the barrier heights, because you plot the log of the width as a function of 1 over temperature, and you get the barrier heights, a standard problem in chemical physics. However, as you are in the very low temperature regime, you're not going to have this Kramer's problem of going across the barrier, but dissipative tunneling. And what the experimentalists found is very interesting, that this has a power law behavior, T to the power 2k minus 1, and that 2k actually is coming from the spectral density of the Bath oscillators. Remember, we had the spectral density for the Bath oscillators in our quantum diffusion problem, and this spectral density, J of omega, for ohmic dissipation is a constant k times omega squared, and you remember you had this cutoff, which I can also put in like an exponential cutoff. And so k is a coupling constant, which has the dimension of the energy, and that's, well, in deference to Kondo because of the mapping of this problem to the Kondo problem. And it's this coupling constant which actually goes into this non-integer power law behavior of the width. Well, so it's surmised, and that has been worked out in detail, that just as for the case of specific heat in solids, at low temperature, it's the electronic contribution that dominates. In this problem also, it's the electronic contribution to dissipation, where hydrogen interacts, or proton interacts with, through Coulomb interaction with the conduction electron cloud, and so that's what gives rise to that. So it's like, so you're really discussing quantum friction, okay? But then, like in the specific heat problem, as you jack up the temperature a bit, the phonons take over, and so there is a crossover, and now you have the phonon dominated until you get into the Arrhenius behavior, which is fully classical. And this turnover occurs around 10 Kelvin, so it's really a very low temperature phenomenon where detailed neutron scattering work has been done here. So that problem can be studied based on this model, which in fact is called the spin boson Hamiltonian by Leggett and Caldeira and others. Well, you can also, of course, consider tunneling in an asymmetric double well, where you don't have the symmetry. In fact, in the hydrogen problem, you actually end up with an asymmetry, and that happens because, you see, the hydrogen goes like an interstitial particle, and it distorts the local surrounding. It creates an elastic kind of a dipole, and these elastic distortions can travel very long range, and so between two hydrogen atoms there are elastic interactions which can actually make the double well asymmetric. So in some parts of the crystal you'll have asymmetry such that the left well is deeper. In some other parts of the crystal the right well will be deeper, and you'll have to average over all of them. And when that happens, you can simply treat that by adding an asymmetry term to the Hamiltonian that I just now described. So it will have Hs as delta sigma x plus epsilon sigma z. And the rest of the stuff is the same. So this causes an asymmetry because this epsilon term means that sigma z equal to plus 1 is different in energy than sigma z equal to minus 1, the difference being simply epsilon. Okay? I have not told you yet that. That requires really hard work. So before you fall asleep, I'll have to do that. I'm not sure that I'll do it really, because let's see how far we proceed. But there are beautiful review articles and now books written, especially by Caldeira and Leggett in Physica, 1983, Journal of Low Temperature Physics, 1982, and then there's a review article, Reviews of Modern Physics, and that is, I think, 1987 by Chakravarti, Dorsey, Caldeira is not there, Leggett, or Garg, Anupam Garg, and others. So that actually is a paper devoted to the properties of the spin boson Hamiltonian, and that's the Reviews of Modern Physics article. Finally, I do want to talk about another issue which is very modern, and that's the problem of a qubit. Hamiltonian as, again, in this generic form, epsilon sigma z plus delta sigma x. Now, also there's some, Professor Anil Kumar's group in IISc, they also do quantum computing in NMR. So if you had a spin half NMR problem, you'd end up with a Hamiltonian like this for the subsystem. For the dot problem, you can also use what is called the tight binding picture. So you basically have a left dot and a right dot. So how do you write sigma z in terms of operators of left dots and right dots? So you can use what are called projection operators. So for instance, the projection operator for the left dot is something like the ket vector L and the bra L, right? That's the projection operator for the LH dot, left dot. So you see, so how do I construct that from sigma z? See, remember, sigma z is a Pauli spin, so it has this structure. So now if I construct half times 1 plus sigma z, so that has really is formed like that. And similarly, half times 1 minus sigma z will be 0, 0, 0, 1. So what this operator is doing is that in this Hilbert 2D Hilbert space, it is just projecting out the sigma z equal to plus 1 state, because this is plus, this is minus, that's plus, and that's minus. So it simply projects that out, right? So if you call that the left state, and so I can write sigma z in terms of that operator, which I'm going to momentarily write. So if I now write epsilon sigma z as epsilon half 1 plus sigma z plus half 1 minus sigma z, and then of course you have delta sigma x. So it is this guy 1 plus sigma z, which is the projection operator in the tight binding limit of what I was writing here, right? Because you just project that state out from the 2D space. So I can therefore equivalently write down that Hamiltonian in the following form. So HS, I can write it as epsilon by 2, okay? Not 2, I don't need the 2 because half goes into the definition of that, minus, because I need half times 1 minus sigma z, the right state. So that's your sigma z. Because, I'm sorry, I should have written a minus sign here. Yeah, was, are you asleep? Why didn't you notice that? And what about sigma x? Well, sigma x is already in this form, 0, 1, 0, 0 plus 0, 0, 1, 0. So that's like saying I have delta times LR plus RL. So that's your tight binding form, okay? But now I want to make life a little more interesting by saying that I want to talk about dissipation in this quantum dot. So what you can do is to say that you add noise to epsilon, noise to delta, and one of the problems that we studied in a collaboration with Israelis, Amnon Aharoni and Orientin Ullman, is to say that this noise is this telegraph process that we talked about yesterday. So epsilon has 2 parts, epsilon plus sigma epsilon, and sigma epsilon is a 2-state telegraph process. It keeps jumping back and forth. But I can now do a quantum version of that problem to motivate this 2-state jump problem, where you say, well, I have also now a sigma epsilon term, sigma z, plus, not sigma, but zeta epsilon, zeta delta, sigma x, and I put in a pseudo spin operator tau x here, okay? And then I introduce, so this is my system Hamiltonian, but my total Hamiltonian now has a coupling a la Caldera-Leggett plus summation k h bar omega k bk dagger bk. So again, by this time you're familiar with what we are doing, that this tau z will cause tau x to flip up and down. But those flips will be time dependent because of this guy sitting there, which are jiggling these bosonic fields. And so the classical limit of this problem is really the 2-state jump process, where both zeta epsilon and zeta delta are these Poisson distributed jump, 2-state jump processes, where the jump between sigma zeta, zeta epsilon and minus zeta epsilon at random instants of time. Do you follow this? Because as tau x flips from +1 to -1, you have zeta epsilon term, zeta epsilon times tau x would be taking values +1 and -1. Okay? So effectively what you have done is that you have added a noise to epsilon, because this term gets added because they both multiply to sigma z. So I have epsilon plus tau x zeta epsilon, and that term will keep on flipping. So with a student, integrated master student in IISR Kolkata, who is now in Göttingen doing Ph.D., Ibad Kamil, we actually did the quantum problem and answered the question under what limit you recover the problem that we had earlier done with the Israeli group, where we had just a 2-state telegraph process added to the bond term as well as the site term. This is a site term and is also called the bond term. Huh? So tau x and tau z are what are called pseudo spin operators. See, any two-level system can be mapped into Pauli spin operators, okay? And they allow you to do your algebra efficiently. So it's just a mapping, just as, if I keep forgetting your name, Sujit. As Sujit was saying, that, when we talk about two-state, though, you're talking about two, let's say, spin up, spin down states or two states in a double well, but the other two states are like, quantum two-level atom. So any two-level system can be described in terms of these Pauli operators. And since you want to go near our classical description where you had a two-state jump process, you introduce fictitious Pauli operators to see whether the quantum mechanics of that system has any limit under which you recover the results for the classical stochastic problem. So that's the meaning of taus. Taus do not have any physical meaning. Taus are like just projection operators. Okay? Entanglement is just the overlap of the wave functions, okay? In the bonding and the anti-bonding states, as Pauling, as Pauling talked about. It has got no classical analog. I have an explicit noise on the sigma z term, explicit noise on the sigma x term. So that was your stochastic, it's partly quantum mechanical, partly completely classical stochastic. And for zeta epsilon and zeta delta, we assumed a two-state jump Markov process or a two-state telegraph process, right? And we actually have this detailed paper in PhysRev B, 2010, I think, where we talked about under what condition you can have dissipation-less decoherence or decoherence-free regions also you can construct. So that was our goal. That even though you have noise, you would think that everything is very decoherent, but we actually discovered some projected states in which you still can recover the initial information on the qubit. So the initial information, so you start with an arbitrary wave function, which will have one component on the L, the other the R, and you have arbitrary phase factors and things like that. And the whole idea of quantum information is to say that at a very long time later, is there something that still retains the memory of the initial wave function? Normally, if you have dissipation, you have no information. The information is completely lost. But we actually could find tricks of playing with this noise trends to see that there is actually a decoherence-free region. So that was a calculation using the kind of master equation that Abhishek was writing, where you have dp dt is Wp, but in addition to Wp, you also have systematic quantum evolution. You see, in these problems, you have systematic quantum evolution impeded or interrupted by stochasticity, the W business of Chapman-Kolmogorov. So it's a combination of the two. So you start writing master equations, but actually you start writing the Liouville equation of the density operator. And we did those calculations. So your friend Ibad, the project he did is to see that can we do the full quantum problem, and under what limit of going to high temperature, etc., some of the results of our calculation here can be recovered. So that was the project. Yeah. There's no need. People have worked on Gaussian noise. See, like, in quantum mechanics, you only solve few problems like either free particle or harmonic oscillator or hydrogen atom. When it comes to noise, you either solve a Gaussian noise or a two-state telegraph noise, okay? And very few things in between. I mean, there are some things called Kubo-Anderson processes, kangaroo processes, etc. So actually, you asked a very interesting question that I was not there in the morning, but Abhishek might have done that Chapman-Kolmogorov equation with this full W. Now, you can't solve that equation unless you assume some special conditions. So one of the special conditions is how from Chapman-Kolmogorov-Smoluchowski you go into a Fokker-Planck equation. So did you do that Kramer-Smoyal expansion? So that W operator is then written in terms of a derivative operator of second order, but there's a formal Kramer-Smoyal expansion, and there's a general result that if the expansion gets truncated at second order, then that's it. Otherwise, you have terms to all orders. So if it does get truncated to second order, then you recover a Fokker-Planck equation from the general master equation. So the Fokker-Planck equation actually describes diffusive processes where you have, in the language of collision physics. So, the earlier days people used to do in astrophysics, gas phase spectroscopy, where you have an optically active atom in a gas, and you have an optically active atom which is then being perturbed by the surrounding particles. Now, you can physically think of two situations in which one is that the active atom is rather fat, okay, and the other guys are small. This is like the Brownian picture, where the small particles kick this large particle, but the cumulative effect of those kicks is a linear viscous drag term, which is linearly proportional to the instantaneous velocity. That's called the weak collision model in gas phase spectroscopy. Okay. It turns out that P.W. Anderson actually did his thesis on this problem in 1954. So that's like the weak collision model. So it is the weak collision limit where you have a Langevin equation in the equation of motion sense, or in the phase space description you have the Fokker-Planck equation. So that's one limit we guys solve problems. It's like one of those generic cases in quantum mechanics like harmonic oscillator, hydrogen atom we solve. The other one is strong collision, where imagine this particle is a tiny one and they're really being kicked around. I mean, a hell of a lot of kicks. So that fellow gets completely, bamboozled by those kicks. I mean, completely randomized. So the velocity prior to the collision has no memory of the velocity after the collision, and that's called the strong collision picture. So strong collision picture is like the infinite version of this jump models, where even here, whether you stay at plus xi epsilon and minus xi epsilon, it's completely uncorrelated. So it's a two-state case, but you can have a multi-state such strong collision models. And it is only in these two limits that the Chapman-Kolmogorov equation does have analytic solutions. And in between, life is very complicated. So it's the same kind of complications that you have in solving partial differential equations. So there is no other reason other than this telegraph noise is actually also common because you can generate that in the laboratory. In the computer, you can generate it too now, telegraph noise. As you might have already appreciated, that there are just two ways of doing these problems. One is using the Heisenberg-like picture, where you use quantum Langevin equation for dynamical variables, or you use a Schrodinger picture where you start in the probability space, right? You write down equations for the probability, like either the diffusion equation or the Fokker-Planck equation, the Chapman-Kolmogorov-Smoluchowski equation, etc., etc. So how do you do that in quantum mechanics? So in quantum mechanics, of course, the analog of the probability function is obtained from what is called the density matrix. So the density matrix actually comes from the projection of a Schrödinger wave function, right? So for instance, rho of t is this projection operator. And the Schrödinger equation says that d dt of psi t is equal to minus I over h bar. I'm still old-fashioned, so I keep my h bars. The Hamiltonian times psi of t. Right? So that's your time-dependent Schrödinger equation. So from this equation and the equation for the corresponding bra vector, and since this guy is Hermitian, you don't have any h dagger, but you flip the sign of that term. You can derive this von Neumann-Liouville equation, which says that d rho dt is minus I over h bar, the commutator of h with rho of t. Is it obvious from these two results? Is it obvious how you get this from using the Schrödinger equations of this form? Okay? Huh? Yeah. But I guess all of you have seen this before, haven't you? Okay. I mean, you have similar Heisenberg operator equations where this sign is plus, dA dt is the commutator of I over h bar, commutator of h with a. Density operator, of course, you have the negative sign coming from this sign here. So what is the formal solution of this equation? The formal solution is that rho at t, and let me put a cap there to indicate that it's a quantum operator, exponential minus I over h bar ht rho at time t equal to 0 right? Okay? Now, as I said, that very often you do spectroscopy, and so it's not for nothing that we spend time taking Laplace transforms and things like that, right? Because to make contact with the experiment is actually the Laplace transform that you are doing all the time, either Fourier transform or Laplace transform. So it makes sense to take a Laplace transform of rho of t. Essentially what we are after is the following. You see, we have a problem now. We have a problem because your Hamiltonian is quite a complicated Hamiltonian. It has got your Hs, Hi, and Hb, and I don't know how to handle this because H is not diagonal in the representation in which Hs and Hb are simultaneously diagonal. So you don't know how to exponentiate these matrices. But the very fact that you want to call it an interaction, you would like to develop some kind of a perturbation theory in which Hi in some sense is treated perturbatively. But the problem in quantum dissipative system is that somehow you must also go to the strong coupling regimes, otherwise things are not interesting. I mean, this is the problem, of course, in strongly correlated systems also, because you don't have an expansion parameter so easily. So we have to develop, clever perturbation theories where you can actually go to the strong coupling limit. But we don't know how to do that yet. And so the task is actually to play with these exponential operators. Okay? Now, of course, you have seen many things, like you have seen in quantum mechanics that if you have IH bar HT, then you write it as minus IH bar HS plus HB because they commute, and then you get a complicated operator. And the idea is to develop this in a kind of a series with HI, right? However, the problem here is you have such entangled operators on the left, such entangled operators on the right, and you have a clumsy mixture of them, and eventually you have to do some kind of trace operations because you are going to calculate averaged of quantities. What are the quantities that you would like to calculate? For the spin boson problem, we have already introduced this. You may want to calculate a correlation function, or you may want to calculate what is called a stay put probability. All these things are measurable in experiments, which is half times, this is really the projection that I was talking about to one of the states. So these are the quantities you would like to calculate. And so, you see, eventually you want to do expectation values of these operators in thermal equilibrium, because that is what is relevant for structure factor, for response functions, and things like that. So eventually you would like to do some kind of a tracing or averaging over the path degrees of freedom, and that gets quite hairy if you have expansion here and expansion there. Okay? And because you want to do things in either the Fourier space or the Laplace space, you might want to take a Laplace transform of this operator to begin with. But you don't know how to take a Laplace transform of something which is to the left and what's to the right. Both are time dependent. Okay? So the trick is, and this is something that you may or may not have seen, is to introduce what is called a Liouvillian operator. Okay? So you can write this term formally as minus I times L times rho of t, where L is called a Liouvillian. It is such that L, see, just as in quantum mechanics, an operator operating on a wave function gives you some value alpha A times the wave function back again. In the case of a Liouvillian operator operates on A and gives the corresponding commutator of the underlying Hamiltonian with A. So it's a dyadic operator. It operates in a higher dimensional Hilbert space. Okay? So is there anybody who has seen a Liouvillian operator before? In what context? NMR. Fantastic. Huh? My class. So, though you may say that, why do I need this? Why do I want to make my life complicated? I said you want to make life complicated because when you develop this e to the IST as some kind of a series, you have this time-ordered series. Have you done this interaction picture Hamilton perturbation theory? You get this time-ordered series from the left, a time-ordered series to the right, and a combination of that, and then you are doing averaging, gets life to be complicated. So what you do is you complicate life at the very first step and simplify life later on. The price you pay is that you now operate in a product Hilbert space. If the Hilbert space of the system was of dimension n, then you are operating in a space which is n squared. So for the sigma problem, for the spin boson problem, your original Hilbert space was 2 by 2. The Liouvillian space will simply be 4 by 4. So you'll have to deal with 4 by 4 matrices eventually. Of course, you will also have to average over the Bath part of the Hamiltonian, and that's in the infinite dimensional space. So remember, this was your HI, and then you have the Bath Hamiltonian. So, and I'll also tell you why the Liouville operator makes physical sense, because our friend is doing NMR or in any kind of spectroscopy. You see, suppose this operator is this projection operator. M and N are the eigenstates of, let's say, some discrete set of levels. And in every time you do spectroscopy, you're actually looking at transitions between these. You never measure absolute energy. You always measure the difference in energies. These are the transition levels. I mean, either you look at the Rydberg lines in hydrogen atom or whatever, you're always looking at transition frequencies. So now if I have a Liouvillean operating on that, this is therefore the corresponding H commutator with this projection operator. And so I have H operating on M minus M N H. That is the expansion of the commutator. And because I have taken these states M and N to be the eigenstates of the underlying Hamiltonian, H operating on M gives you the energy eigenvalue corresponding to that state. So I have therefore Em minus En times Mn. So very nice, because then it's saying that the Liouville operator operating on such a projection actually gives you the transition frequencies, because if you divide by h bar, that's the measurable thing. So the eigenvalues of Liouville operator are actually the measurable quantities, the spectroscopic transition lines. So therefore, in spectroscopy, in all these chemical physics type problems, people use Liouville operators quite extensively. And you can see why it makes your life now very simple when you try to do Laplace transforms, because using this commutator relationship, I have this relation, right? Because I can formally expand e to the minus ILT. If you formally expand, then you get 1 minus ILT plus minus I t squared L squared dot 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 rho of naught. And so each term is like a commutator, and that's the same expansion as rho of t here, because if you expand this, you get all these nested commutators. You know, this expansion is, first term is rho of 0 plus minus I by h bar t h commutator of rho of 0, then all these higher order terms, minus I squared, t squared over h bar squared, all these nested commutators, right? So same thing you would get by writing it in terms of a Liouvillean and using the commutation properties, right? Okay? So now you formally take a Laplace transform. Again, as I'm saying, it's physically motivated because that's how you do experiments. In most spectroscopy experiments, you're actually taking a transform over time, because you're measuring things in the reciprocal space of the frequency. When you have X-ray, you don't do it in the real space, you do the reciprocal space of the k vector. Again, you're taking Fourier transforms. So experiments always go into that other kind of space. And so now I formally introduce the Laplace transform of rho of t, which is rho of s or z that you can use the notation of, is integral 0 to infinity dt e to the minus s of t times rho of t. This is a formal definition of the Laplace transform. Imagine, you have to always, of course, tacitly understand that S has got a purely complex part and a real part. And the real part is such that will make the integral convergent. Right? S is, after all, minus I omega plus delta. And when you want to recover something like this, you will have to do the calculation and then go to the delta equal to 0 limit. But that term is necessary to keep the things under control. So formally, the Laplace transform I can calculate. It is simply equal to 1 over S minus IL times rho of naught. So it's what is called a resolvent or a green function. Of course, you understand that this is not really S, but S times the unit operator in that space of the Laplacian, the Liouvillian. But L, so let me call this U. It's a Laplace transform of your time evolution operator, which is 1 over S minus I. And L has 3 parts. Just as H is splittable into 3 parts, the system part, the interaction part, and the bath part. And our idea is to make an expansion of this resolvent in terms of Li. Okay? I'm sure you have done Green's function in quantum mechanics. I'm not doing anything very different except that I'm doing it for the Liouville operators. So use the operator identity. Says that if I have an arbitrary operator A, I can write it as 1 over B plus 1 over A, B minus A times 1 over B, or alternatively as 1 over B plus 1 over B, B minus A, 1 over A. Do you see that as an identity? Because you just look at the first term. I have B here, and I have a 1 over B multiplying from the right. So that would simply give me 1, and that's your 1 over A term to the left on the left-hand side. That term, 1 over A and A, will give you minus sign and 1 over B, and that cancels with it, so we have an identity. And same is true with the second formulation, right? Huh? Alpha? No, there's a Liouville, L, sorry. It's script L, not alpha. Script L. But did you see this? Boshak? Hello, Boshak, did you see this? Do you understand this? Huh? So suppose, I mean, this is general operator identity. Suppose we identify A with this full guy. So your A is really S minus I, the full thing, IL. Then what do you get as U of S? So U of S is what you may, so it's now 1 over B, and I call B is really S minus I L system plus bath, because of the fact that HS and HB commute. I want to work in a representation in which they are simultaneously diagonal, so B is such an operator. Therefore, I have U of S, let me use this identity here, is U naught of S. What is U naught? U naught, I mean, I'm writing it as naught because that's like the unperturbed Green's function or propagator, and that's like S minus I Ls plus Lb. That's like 1 over B. Then you have 1 over B, which is U0 of S again, and B minus A. Now A had only an extra term called Li, so when I do B minus La, I simply have I Li upstairs, and then U of S back again. Do you understand that? Have I lost you? Is there anybody who doesn't understand this? You didn't follow. Okay. No, madam, what I'm doing is that I want to calculate the inverse of this operator, right? For doing that, since I'm making operations with matrices or operators, I have to be careful about non-commutativity, etc. But I have this identity, correct? No? This identity is baffling you? No. So I have this identity. So in order to make use of this identity, A and B are arbitrary operators. So I'm identifying A with S minus I L, which is I Ls plus Lb plus Li, and B I'm identifying with that. And so my U of S has been defined like this, which is simply 1 over A, and U0 of S is simply 1 over B, right? Because I've identified this with B. So I get 1 over B, then I have B minus A, and B minus A is simply picking up that interaction term that is upstairs, and then I'm back again at 1 over A, which is that term, right? But in order to develop it in a series, you do what is called iteration. So you see, for U of S, you're going to now substitute back again. So I have U naught of S plus U naught of S ILI times U naught of S plus U naught of S ILI U naught of S dot 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 dot. Right? So I have now developed a series. Have you seen this? This is sometimes called the Dyson-Lippmann-Schwinger series. So the series is the following. Is a free propagator. See, my total propagator, the first term is a free propagator. Then I have free propagator times the interaction terms times the free propagator back again. Then free interaction, go on in an infinite series. Okay? So this is another way of doing time-dependent perturbation theory that you might have done in your MSc quantum mechanics. of S operating on rho at time t equal to 0, where U of S has this junk on the right hand side, this complicated series. But eventually you want to do averaging, all right? So what is it that you do here? And this is a question that I think came up, Abbas asked me in the context of quantum Brownian motion also, that very often you use what is called the factorized initial condition, which is that your rho at time t equal to 0. This is, by the way, the full density matrix, the complete many-body density matrix. So you say that rho factorizes at time t equal to 0 into a system part and a bath part. Because HS and HB commute with each other, I have no problem in factorizing them. That's the initial condition. And you let the trajectories evolve, and of course you're going to get entanglement or mixed up states because of HI. And for rho B, just as in the context of quantum Brownian motion, you assume that the bath is at a fixed temperature, so rho B of naught is given by this Gibbs measure, e to the minus beta HB over the partition function, where beta is 1 over kBt. Okay? And for rho system part, either you can start from an arbitrary initial condition, or you can imagine that your system was also in equilibrium with the bath at time t equal to 0. For instance, when you calculate such correlation functions in equilibrium, is a chain given just that you don't fall off? Or? But this chain may not hold my weight, I think. It's only meant for Abhishek, Dhar, and Sanjib, Sabhapandit. So when you measure correlation functions in equilibrium, like in neutron scattering or hydrogen in metals, then your system is also in equilibrium at time, because you're measuring equilibrium correlation functions. When you measure something like this, a stay put probability, you may want to put an arbitrary initial condition, subsystem density operator. But this bath guy is always such a large fellow that no matter how many times you kick it, that fellow recovers pretty rapidly its equilibrium, and it remains therefore, and that's an assumption, because you are going from a reversible equation of motion to a situation where you want to discover irreversibility. So your bath is therefore assumed to be at constant temperature ever. Okay? And now, therefore, what you would like to do is that, you see, you want to do what is called a partial tracing, because remember in the quantum Brownian motion problem also, we wrote down the equations of motion for your particle of interest, like little p's and little q's, and also wrote down equations of motion for this jth balls, like pj's, qj's. We integrated out the pj, qj terms and put them back into the equation of p and b. So in a sense, we were projecting out those degrees of freedom, or integrating out those degrees of freedom. The analog of that would be doing thermal averaging over the bath variables, leading you to what you may call a reduced density operator. A reduced density operator is an density operator for your system alone, rho capital S, which is obtained by partially tracing over only the bath variables of full rho of t. You follow? Now this is not a full trace that you would need to calculate expectation values, but this is only a partial tracing over the bath degrees of freedom. Okay? So you have, this is called the reduced density operator. And so my reduced density operator, and in particular its Laplace transform, don't get confused between this capital S, which is for the system, and this little s for the Laplace transform, which is now trace, and having used the factorized density operator method, you have trace B U of S rho B times rho S at time t equal to 0, and this is what you want to calculate. So you want to calculate a partial averaging of this propagator weighted by the Gibbs measure. So that is the task at hand, right? So the task at hand is actually to calculate this guy, and once you are done with that calculation, since you have already taken the trace over the path in a formal sense, you have to do that hard work. But after you have done the hard work, that operator is an operator only in the space of the system alone, right? Because you have integrated out, or you have summed over the path variables. So that would be like a finite dimensional matrix. For our spin boson problem, that will turn out to be a 4 by 4 matrix because you're dealing with the Liouvillian. But you have done the other hard problem of averaging over the path variables. It is simple because in the Caldera-Leggett and the Ford et al. Swansea et al. Problem, your bath is a harmonic bath. So that's why some of these averages are done rather simply. But that work still needs to be done. And then you have to, then of course 4 by 4, either if you have tenacity, you do it by hand, you have to invert 4 by 4 matrices, or you go to the computer. That's a simple task. Okay? I think now we should have a break. It's 4 o'clock. We should have a break, and then we reassemble when the two directors of the school should tell us.